In this example, we're going to be matching the slope fields to the different differential equations on the next page. There's a few different ways to go about this. One of the ways that you can try to work these problems is you can try to sketch a possible solution to each one of these slope fields. Let's start with A. So in part A, I'm just going to arbitrarily pick, I don't know, maybe this point down here, and then I'm going to try to draw a curve that fits this slope field. You can see that part A looks to be quadratic. So what we can do is we can go to the next page, which is what you're supposed to match to. And what we're going to look for is we're actually going to look for a linear equation. The reason why is if we go back to the slope field, the red graph is actually the solution to dy dx, which is the original equation. You have to find the antiderivative of your differential equation to give you a picture of what the graph is going to look like, the graph in red that we just drew. So what I'm looking at here is I'm looking at probably number 2. If we find the antiderivative here, I'm going to wind up with y is equal to x squared plus 4x plus c. I can scroll down even a little bit further. E to the x won't work. 2 is a line, but it's not linear in terms of having a variable. And it's going to turn into a linear if we find the antiderivative. So if we look at, let's see here. Ooh, I see one right now. Number 8. Number 8, it looks like if we find the antiderivative, we're going to wind up with x squared. It's supposed to be an x. Let's just erase that a little bit. See if I can erase that for you. There we go. So that's going to be x squared over 2, then plus c. None of the other ones here will wind up if we find the antiderivative being quadratic, which is what we're looking for. So we've got number 8 to choose from, and we've got number 2 to choose from. And the key with picking which graph matches or which equation matches the slope field is to take a look at a few things. Number 1, number 8 here does not have a horizontal shift. The vertex is at the origin. Also, we can take a look at the 1/2 as our leading coefficient. So that'll be this guy right here. Put a 1 in there if you need to. That 1/2 is going to widen out the parabola. Now let's take a look at number 2. Number 2, you can see here that if we wanted to, we could complete the square. So I would add 4 here and then subtract 4 as well. And we've got x plus 2 squared and then plus another constant. Whatever c minus 4 is going to be another constant. So you can see this is a shift left now by 2 units, whereas the previous, or the one number 8 down there, did not have any horizontal shift left or right. So if we go back to A, it really seems like A is looking like it has a horizontal shift of left, and we don't know the scale here. So the scale could be, we could have -1 right here and -2 right here. So there very well could indicate a shift left too. And the vertex of this thing is definitely not around the origin. So if we go back to our list, we're going to put letter A down for this one. Definitely matches. As we continue on with these, I'm not going to ruin all the fun for you and do every one for you, but I will help you with this, of course. And so let's go ahead and draw the shapes of the antiderivatives of those differential equations. So this one right here is going to look, seems like it's going to be probably exponential, and you can pick. This might not be the best one to pick. As a matter of fact, here I'll go ahead and erase that and draw something a little bit better for you. It doesn't really matter, I guess, but as we pick this curve right here, this one kind of looks exponential. So this is going to be exponential. We said this was a quadratic. You can write a note down to yourself if you want. This guy over here, if we try to draw a graph that matches all of those slopes, this one looks, now it's not a great graph, but it'll do. This one looks to be cubic. And once again, this is the antiderivative or the solution to those differential equations we saw below. Let's keep going on with the rest of them here. Here we've got something that could be sinusoidal. Could be cosine, who knows? Yeah, there we go. There's a nice little graph right there. So this guy has a center right here at the origin, and or the midline crosses right here at the origin. So this one's probably going to be a sine curve. So we'll do the sine of x. And then here, this is an interesting one. There's a few different ways that you could draw a solution curve to this. I'm just going to draw one over here. So this one's going to look kind of like, and this might even go up further a little bit like that. This one looks like the natural log, but it's flipped. So normally the natural log function would look like this. And so this one's reflected over the x-axis. Come on, erase, there we go. So we know that this might be something like the opposite of the natural log of x. The reason why you see this shape over here is because we would usually write this with the absolute value as the antiderivative here. Moving on to part F. Now part F, this one's looking kind of quadratic to me. Try to draw this a little bit better for you. There we go. And it's kind of widened out a little bit compared to the other one. So actually I might just skip ahead and go down to my differential equations, and we're gonna match this with F. Also looks like that origin could be at the vertex, I should say, could be at the origin or shifted anywhere up or down. Definitely the x value is 0 for the origin for this one. We'll move on with G, H, I, and J. So G looks like a parabola that's facing downward. So this one's going to be quadratic with a negative leading coefficient. Maybe that's the case. Over here, we have a function that almost is straight vertical here. And then as we go down, kind of follows a pattern just like this. I don't know if you're starting to see the shape a little bit. So this one happens to be quartic, or you're going to see something raised to the 4th power here in the solution. So we would call that a quartic polynomial. And we have a nice curve here. Looks sinusoidal again, but this one I think is going to be the cosine, and we're probably going to have a negative cosine here because it looks like the bottom is right here. Right there's the bottom of this thing. So if we go down to J, then this one looks like just a line right here. So you can go ahead and draw a straight line. And we can now start matching these up. To do that, I'm going to do a few of these with you, just a couple more, and then I'm going to lean on you to do the rest. And you can check out the completed notes online. So let's take a look at the antiderivative of the sine of x here. So the antiderivative would be negative cosine x plus c, of course. So this is what we want to match up to those graphs above. So we're going to take a look and see if we can pick that out. And that looks like I for sure for that one. So if we go back to matching, I can write myself an I right here. You can write that down. And you can go through the rest of these. And the key here is to find the antiderivative of each one and to match those up. You can also match the slopes up. So let's take a look at number 4 real quick. So dy dx is 2, which means that the x and the y don't matter, that the slopes of the tangent lines are always 2. So if we take a look at the graph here that matches it, it happens to be J. These lines here, all of these lines have a slope that's the same. So we can also kind of reason through this a little bit differently and come to a conclusion without having to find the antiderivative. If you did find the antiderivative for this one, that would be 2x plus c, which again is the shape of the red line that you're going to see in the slope field there. So that looks to be about the case.